Welcome back to Applied Mathematics. In this video, I want to work through the idea of propagation of error. This mouthful of a title describes the concept of determining how precise a calculated value is given the accuracy and precision of the initial measurements. Or if you are trying to figure out the tolerance of a final result and you need to work through what kind of accuracy and precision do you need in the original calculation. There are two rules, aptly named the accuracy rule and the precision rule. Let me get my head out of the way and let's start in. The precision rule tells us that when adding or subtracting, keep the precision of the least precise measurement. And if you stop and think about it, that makes perfect sense. Consider the example here of 170 inches plus 0.25 inches. All right, 170 inches. That is the width or the length of a wall in a large room. 0.25 inches. That is, I don't know, the width of my cell phone. But look more so at the accuracy and precision. My 170 inches measurement only has two significant digits. So I am saying that this measurement is somewhere between 160 and 180. Essentially, I've measured to the nearest foot, and I've reported the result in inches anyway. If I could be off by as much as 10 inches, adding a quarter of an inch to the measurement doesn't do anything at all. So 170 inches plus 0.25 inches is still to within the tolerance that we measured it, 170 inches. Getting a little bit more careful here, 170.0 inches plus 0.25 inches. Now, my 170-inch measurement, the length of a wall, I have very carefully measured to the nearest tenth of an inch. And so when I add these values together, that quarter of an inch has an impact. Sure, my calculator tells me that when I perform this calculation, I get 170 plus 170.25 inches. But that's still more precise than I really have. Right? This measurement is to the nearest tenth of an inch. This measurement is to the nearest hundredth of an inch. The least precise measurement is this one, 170 inches. So that's where I'm going to round. I take my result of 170.25, I round to the nearest tenth of an inch, and I call it 170.3. Right? That is the precision rule. We use the precision rule whenever we are adding or subtracting. Those are the only times we use it, and we use it every time those situations come up. The caveat to this rule is that exact values have infinite accuracy. I need to be honest, I'm not entirely sure what an exact value looks like in something that could be added together. I can't come up off the top of my head with any examples of adding an exact value to an approximate value. But if you were going to, you just ignore the exact value and round based on wherever the approximate value is already rounded. That will be more important in the accuracy rule that we'll look at next. The accuracy rule says that when you are multiplying, dividing, raising an approximate base to an exact power, or evaluating a radical. That is a very cumbersome way of saying exponents and roots. Technically speaking, this doesn't work for all exponents and roots. We are not going to come across any of the exponents or roots where it doesn't work in this course. But if you continue onward, you might see them in a future mathematics course or physics course or somewhere else. Whenever you're multiplying or dividing, no matter what, and then exponents and roots, in most cases, there's a couple of weird corner cases that can come up that you'll see in the future, not here. Round your result to have the same accuracy as the least accurate measurement. So if I want to calculate an area, and the area is 3.5 feet by 1.75 feet, well, my calculator, as always, is happy to tell me that 3.5 times 1.75 is 6.125. But that's not the end of the story. 6.125 has 4 significant digits, and that's way too many. The numbers that I started with have 2 significant digits and 3 significant digits. The worst accuracy is 2 significant digits, so I'm going to take my 6.125 and I'm going to round it to have 2 significant digits. In this case, that will be 6.1 square feet. By coincidence, this particular example gave us a result that is rounded to the nearest tenth of a square foot, where my starting value was rounded to the nearest tenth of a foot. That does not always happen, and in fact, very often will not, but the number of significant digits is the thing that matters. Taking one more example, right? If I have 9.63 inches and I want to multiply that by 8.475 inches. Again, my calculator is very happy if I don't typo it, my calculator will be very happy to perform that calculation for me. And my calculated result has 6 significant digits, which again is way too many. Looking at the two measurements I started with, I have 3 significant digits. I have 4 significant digits. The worst of these is 3 significant digits. So I'm going to round my result to have 3 significant digits. In this case, it comes out at 81.6 square inches. Just like with the precision rule, with the accuracy rule, if you have an exact value, then we can assume that it has infinitely many significant digits. And multiplying by an exact value is actually fairly common. Unit conversions are exact values, right? 1 mile is exactly 5,280 feet. So if I want to take the measurement of 28,000 feet and I want to convert that into miles, I'll multiply by 1 mile over 5,280 feet. I realize that's going to be a division problem. So I ask my calculator, what is 28,000 divided by 5,280? And I get this horrible decimal value. 5,280 is an exact value. We ignore 5,280 when we're trying to come up with where to round this. We look at the one measurement in the calculation, 28,000. We realize it has 2 significant digits, and we write our result as 5.3 miles. I think that this example of unit conversions really shows why the accuracy rule is what it is. I mean, yeah, sure, we can do the calculations with mixed measurements, but the rule down here, why is my green screen so terrible? I apologize. Um, I don't have time to fix it right now, but I want it to be better in the future. Anyway, this calculation, 28,000 feet to the nearest thousands of feet is 5.3 miles to the nearest tenth of a mile, right? 1,000 feet is about a tenth of a mile. It's actually closer to 2/10 of a mile, but to within a quick approximation, it's about the same thing. So that's where the accuracy rule really comes from. And I think that's the place to help you remember it. When you're doing a unit conversion, right, your accuracy in feet, nearest thousand of a feet, Nearest thousands of feet, your accuracy in miles, nearest tenth of a mile. 1,000 feet and a tenth of a mile is approximately the same distance. So it makes sense that your measurement tolerance comes out the same either way. And that's kind of what I think of, that's what I keep in my head to try to make sense of why the accuracy rule works the way it does. All right. Before I wrap up on this video, one more example of the accuracy rule. Actually, let's just do two real quick. I said exponents and roots. Exponents are a little bit tricky because the base can be an approximate value. Let's say 4.83 seconds. Let's say 0.483 seconds. The exponent has to be an exact value, squared in this case. My calculator will be happy to take 0.483 and square it and tell me that comes out at 0.233, etc. We're going to round that and call it 0.233 square seconds. What is a square second? I don't know or care. Likewise with square roots. If I want to take the square root of 1576 square miles, my calculator is happy to take the square root of 1,576. It comes out at this horrible decimal number, but I know that I can round it to have 4 significant digits. That is going to come out at 39.70. Right, 698 rounds up to 70. And the 0 after the decimal point is a significant digit. So we still have 4 significant digits, which is what we were after. All right, I think that wraps it up for this one. As always, thank you for joining me, and I'll see you next time.